the star number Y in the constellation the Swan, and in modern terms found it to be about 10 light years from Earth, as compared to the mere 8 light minutes distance of the Earth from the Sun. Only the very closest stars had parallax large enough to be measured in this way in the 19th century. And it was only our own galaxy that was mapped out by astronomers. In those days, in the 19th century, as far as astronomers knew, that was the whole universe. Our galaxy, that was it. There were clouds here and there that were visible, called nebulae, using the Latin term. Nobody knew what they were. In fact, they were somewhat of a nuisance for astronomers who were looking for things like comets, in which they were really interested. In 1912, Henrietta Leavitt was observing a cloud in the smaller Magellanic Cloud. Well, she was observing a cloud called the smaller Magellanic Cloud, first noticed by Magellan in his trip around the world, and found in it variable stars called Cepheid variables. And she could see, since all these stars were about the same distance from the Earth, the smaller Magellanic Cloud was only so large, she could see that the intensity of the light from each one of these stars was strongly correlated with the period over which their light oscillated. So that by observing the period of a Cepheid variable, you could judge how far away it was, because you would know how intrinsically bright it was. Of course, you had, in order to calibrate this distance scale, you had to know how far away the smaller Magellanic Cloud was. It's an outskirt of our galaxy, a kind of satellite of our galaxy. That was done, and in the years following Leavitt's work. And then in 1923, Edwin Hubble discovered Cepheid variables in another cloud, the large nebula in the constellation Andromeda, that astronomers know by the beautiful name of M31. And using Leavitt's calibration, using Leavitt's relation between period and luminosity, was able to work out the distance of M31 and found it was about 1 million light years from Earth. Actually, that was not a very accurate measurement, and after World War II, Bada and others recalibrated the Cepheid period luminosity relation and found that M31 was about twice as far as Hubble had estimated. But in a way, that wasn't important. The important thing was that Hubble had discovered that this cloud, the Andromeda Nebula, was a galaxy in its own right, quite as large as our own. And you could see many other galaxies throughout the sky. And suddenly the scale of the universe expanded enormously. Our parochial view that our galaxy was the whole universe was destroyed. We saw that we were part of a much larger universe with galaxies, and as Hubble also found in the late 1920s, rushing away from us in all directions. We learned that the universe was a gas of galaxies in uniform motion, rushing away from any given point in a uniform expansion, extending out to millions and indeed billions of light years. We now see galaxies out to 1 billion light years, and perhaps even more. But we are running into a limit. We will never see anything beyond about 10 billion light years because the universe is only so old. This expansion can be traced backward in time. We know that it has been going on for about 14 billion years. And so we can never see anything that's much farther away from us than about that many light years, 14 billion light years. We have no doubt that the universe extends outward much farther than that. There's no reason to believe that our horizon limits the actual size of the universe. And for all we know, and indeed many physicists think, as many physicists think is true, the universe is infinite in size. Now, progress in extending the scale of familiar distances down to shorter distances has been much slower, but at least in this century has gone much farther. Many more orders of magnitude down in distance scale than we have been able to go up. Democritus, in about 400 BC, speculated that all matter is composed of atoms. He had no good grounds for the speculation, and he certainly had no idea how large atoms were. All he knew were that they were too small to see. In the 19th century, that became a major concern of physicists and chemists to try to estimate the size of atoms. Now, you can measure the density of ordinary materials. For example, a cubic centimeter of water weighs about 1 gram. If you assume that the water molecules are packed close together, then that must also be the density of water molecules, roughly speaking, within perhaps a factor of 10. They must have a density of about 1 gram per cubic centimeter. So if you knew how heavy they were, if you knew the mass of a molecule, you would know its size. But no one knew the mass of atoms or molecules. What physicists and chemists were able to do in the 19th century was to measure a lot of ratios. They could measure the ratio of the mass to the electric charge of an atom by observing how much electric charge was needed to produce a given weight of material in electrolysis. If you knew that you needed an electric current running at 1 ampere for so many seconds to produce 1 gram of silver plated out on an electrode in electrolysis, then you could estimate that the ratio of the unit of electric charge, whatever it was, which we now know is the charge of an electron, to the mass of a silver atom was something. But nobody knew what the charge of the electron was. there were other ratios that were measured, but it was frustrating. A lot of accurate measurements were made, but no one could get down to an individual quantity like the mass or the size or the charge of an individual atom. There were crude estimates made from the viscosity of fluids. Viscosity is stickiness, the phenomenon that fluids resist being rubbed against each other, because when you try to do that, momentum is carried from one part of the fluid to another, and the rate at which momentum can be carried from one part of a fluid to another depends on how far atoms can travel without encountering other atoms, and that depends on the size of the atoms. And by measuring the stickiness or viscosity of fluids, in particular the air, Loschmidt in 1865 was able to make an estimate that the size of the air molecule was about a 10 millionth of a centimeter, 10 to the minus 7 centimeters. By 1900, however, finally precise measurements were made. For example, of individual atomic properties. For example, the charge of the electron was accurately measured in Millikan's oil drop experiments. And using that together with data from electrolysis and a lot of other measurements, Einstein's work on Brownian motion, Planck's work on black body radiation, we had precise measurements of the mass and electric charge of atoms and ions, and it became known with fair accuracy that atoms' size is about 100 millionth of a centimeter, a scale of distance which even was given its own name after a Swedish spectroscopist, was called an angstrom. But that wasn't the end of the story. At first, it was thought that these atoms were like puddings of negative electric charge in which electrons circulated. That they were puddings of positive electric charge in which electrons circulated so that the atom as a whole was electrically neutral. In 1911, in experiments at Rutherford's laboratory in Manchester, it was found that that's not right, that in fact, the atom is mostly empty space. Electrons revolve in the atom like planets in the solar system traveling through largely empty space. And at the center of the atom is a tiny object having almost all the mass and positive electric charge of the atom that we call the nucleus of the atom. This was discovered by scattering charged particles called alpha particles on metal targets. And it was found that sometimes these particles would be repelled backward from the surface of the metal. This was very surprising because these were highly energetic particles emitted in the radioactive decay of the element radon. And it was hard to see how anything in the atom could knock these charged alpha particles back. In fact, you could argue, just on the basis of the conservation of energy and momentum, that in order for them to be knocked backward, they had to be hitting something heavier than they were. Just as a bowling ball rolled into a soccer ball cannot bounce backward because it's heavier. A soccer ball rolled into a bowling ball can bounce backward. So Rutherford concluded that the alpha particles were hitting something in the atom heavier than they were. And furthermore, they had to be getting very close to it, because if the forces repelling the alpha particles were electric forces, he knew how close they had to get to the charge of the nucleus in order to be stopped in their tracks and sent backward. And that distance was a small multiple of 10 to the minus 13 centimeters. In other words, a 10 trillionth of a centimeter, smaller than the size of the atom itself by a factor of about 100,000. So immediately the scale of distances that were being studied by scientists had gotten finer and finer, first down to 100 millionth of a centimeter, the size of atoms, and then to a 10 trillionth, 100,000 times smaller, the size of an atomic nucleus. Now that's about the smallest size about which it's useful to talk about size. Things smaller than that, things like electrons and other elementary particles, really don't have a very well-defined size. This is because in order to study an object, you need some kind of wave with a wavelength that is smaller than the object. For example, if you want to study an atomic nucleus, which has a size of 10 to the minus 13 centimeters, you need to probe it with radiation of some kind or other, some kind of wave, with a wavelength less than that size, so that the image, if you want to think of it that way, is not hopelessly blurred out by the diffraction of the large wave. If you want to use, I mean, it's a familiar phenomenon. If you want to use radar to examine the size of a distant object, you have to have a wavelength smaller than that object. Now, the trouble is that there's an inverse relation between the wavelengths of any kind of wave, and we know now that particles like electrons and alpha particles, other particles, can be described, we've known this since the 1920s, as waves. There's an inverse relation between their wavelength and their momentum, so that to get to small wavelength, you need high momentum, which means high energy. And that energy can destroy what it is you're trying to study. For example, for the size of a nucleus, if you want to probe it, for example, with a particle like a proton or a neutron, which are the particles inside atomic nuclei, to get to a wavelength that small, you need an energy of those particles about 20 million electron volts. Now, that happens to be the energy at which you will excite and perhaps even destroy the nucleus you're trying to study. So we can study nuclei, and it does make sense to talk about their size, but that begins to lose its relevance when you get to smaller things like the individual elementary particles, the protons, neutrons, and electrons themselves. And rather than talk about their size, I'd rather talk about the wavelength of the light or other radiation needed to produce them, but let's say light. And in that way, consider finer and finer distance scales as we go to particles that are heavier and heavier. The electron corresponds to a distance of about a 10/1000th of a centimeter in this sense. It's called the Compton wavelength of the electron. It's the wavelength of light needed to accelerate an electron to a high velocity. The heaviest particle we know today, the heaviest particle we've been able to study in our laboratories is a particle called the tauon or tau lepton, and it weighs about 1.7 billion times as much, 3.5 billion times as much as an electron, just doing that in my head. And it corresponds to a wavelength of about a small fraction of 10 to the minus 13 centimeters. By going to the highest energies with our present accelerators, we can probe distances about 100 times smaller. Let's say the smallest distances we can probe with our existing accelerators, in the sense that I've described, is about 10 to the minus 16 centimeters. I don't know how to say that. It's a decimal point, 15 zeros, and a 1 centimeters. Now, so that is how far we've been able to extend the area of physics with which we're familiar. And within that range, down to that very small distance of 10 to the minus 16 centimeters, we think we understand what's going on. We have a theory of elementary particles and the forces acting on them called the Standard Model. I introduced the name Standard Model because I wanted to avoid giving it the aura of a dogma that we had to believe in, and yet at the same time giving the impression that this is a theory about which we can all agree to discuss our ideas, our experiments. We already know of small departures from the Standard Model, but it stands firm as an extremely accurate approximation to everything we've been able to probe down to distances, as I said, about 10 to the minus 16 centimeters. And now at these very small distances, we're encountering a terrible problem. It's a problem having to do with the energy of empty space, what is sometimes called the dark energy. It may seem like a silly thing to talk about. I mean, isn't empty space just empty? Well, no, in a sense it can't be, because of a principle of quantum mechanics known as the uncertainty principle. The uncertainty principle is a fairly precise statement. Applied to particles, it says that it's not possible for a particle to have a certain definite value of position and at the same time to have a definite value of momentum. As applied to fields like the electric and magnetic fields, it tells us that it is not possible for a field at the same moment to have a definite value and a definite rate of change of that value. And in fact, it puts a lower bound on the product of the spread in position and the spread in momentum. This is something that was discovered in the 1920s with the advent of quantum mechanics. Now, that means that it's not possible to say that empty space is a region in which fields like the electric and magnetic field are simply zero and remain zero. Because if they have a definite value, zero at one moment, then the rate of change has no definite value. It could be anything the next moment. If we know that they're very small at one moment, then the range of rates at which they're changing must be very large, and they can become very large the next moment. We can work out the energy in these fields in what we would normally call empty space. Now, if you do the calculation, including radiation fields, electric and magnetic radiation, light waves of all wavelengths, you get an infinite answer. That, of course, we can shrug off saying, well, we really don't understand physics at very small distances. But we do understand that physics, as I've said, down to distances of about 10 to the minus 16 centimeters. And if you include radiation in empty space due to these quantum fluctuations down to 10 to the minus 16 centimeters, you get an enormous energy density. Not infinite, but enormous. Much larger than the energy density of nuclear energy within an atomic nucleus, let alone piddling things like the energy density in a tank of gasoline. Who cares? Most physicists would have said, say in the 19th century, that we're never really interested in the value of the energy in anything. We're only interested in energy differences. That's all we measure. For example, we can say that there are so many calories in a cup of sugar, but what we really, in the chemical energy in a cup of sugar, but what we really mean is that there are that many calories in the difference between the chemical energy in a cup of sugar and the chemical energy in the water and carbon dioxide that the sugar turns into when it's burned inside our body as fuel. It's always differences in energy that matter. When we measure the energy of the radiation emitted by any physical system, we measure the energy it had before and after. It's always a difference. So, in a sense, the question of the energy density of empty space is unimportant because space is always with us. We're not going to create or destroy space. But there is one thing in the world that does respond to energy itself, not just to differences in energy, and that's gravity. The source of gravity, as we learned from Einstein, is not just mass, as Newton thought, but all forms of energy, not just the energy E equals mc squared in a mass m, but the energy in anything, including the energy in empty space. And this energy in empty space affects the expansion of the universe. If it is positive, it causes the expansion to speed up. If it's negative, it causes it to slow down. Now, the energy in empty space that we estimate, as I've described, is so large that it would cause the expansion of the universe to be incredibly rapid, vastly more rapid than we in fact observe it to be. Or I could put it the other way around. By observing the expansion of the universe, we can put an upper limit on the energy density of empty space. And that upper limit is vastly smaller than the energy density we estimate by probing nature down to the smallest scales we can reach. So now we come to the fusing of the interests of physicists who study the very large and the very small. By the way, this is just one example. There are other places where these interests come together, and this is just the one that I'm going to talk about. Our understanding of physics down to very small distances indicates that there should be an energy density of empty space, which is many orders of magnitude. In fact, to be precise, 56 powers of 10 smaller than the upper limit imposed by observations of the expansion of the universe. Well, this led many physicists in the 20th century to conclude that if this quantity, the dark energy, the energy in empty space, is so much smaller than you would expect from a back of the envelope calculation based on what we know in the standard model, well, maybe there's some fundamental physical principle that says it's zero. It could be zero because when Einstein developed the theory of general relativity, the following year, in 1917, he introduced a modification of the theory known as the cosmological constant that, although he didn't put it this way, amounts to another contribution to the energy of empty space. And it could be that this constant of Einstein's simply cancels what you get from the quantum fluctuations. Why should it cancel? We don't know, but maybe there was some fundamental physical principle that said they had to cancel. It was exactly zero. In 1998, it was discovered by astronomers that this is not true, that in fact, the expansion of the universe, which had always been thought to be slowing down due to the mutual gravitational attraction of distant galaxies for each other, was in fact speeding up, as could only be explained by an energy in empty space, an energy which could be estimated from the way that the expansion is speeding up to be about twice the energy in ordinary matter, the E equals mc squared in ordinary matter. The universe, the energy of the universe is dominated by this dark energy. It's still vastly less than we estimated from our knowledge of physics at very small scales in the standard model. We don't know why. And this is now, I would say, the most severe puzzling problem facing physics at the most fundamental level. It's a problem that, as I said, brings together physical speculation about the very smallest distance scales. Perhaps they arrange themselves to be canceled by the cosmological constant. And the very largest scales that we can study, at which we actually measure the value of this dark energy. We can think of two reasons, well, probably more than two, but there are two major classes of explanation of why the dark energy, though not zero, is so incredibly small compared to what you might expect it to be. One is simply that for some reason it's decaying with time. And the universe is old and it has decayed a lot so that it's now quite small. We don't know why that should be true, but there's no doubt the universe is old. The other is a more speculative, wild idea called the multiverse, that the universe that we see out to the larger scales we can study, the 10 billion light years or whatever it is really only part of a much larger ensemble of universes that we put together called the multiverse. Many, many big bangs, perhaps an infinite number, in which the constants of nature, including the cosmological constant of Einstein, take different values in a random way. In the vast proportion of those universes, the cosmological constant doesn't cancel the quantum fluctuations. The universe expands so rapidly, there's no time for galaxies or stars to form. There are no people, there are no scientists asking these hard questions. Any scientists who ask questions about the dark energy must, according to this view, be living in one of the very rare, fortunate universes in which the cosmological constant almost cancels the dark energy. It doesn't have to cancel it exactly, it just has to cancel enough of it to allow the expansion of the universe to be slow enough for galaxies to form, and then for stars to form within galaxies and life to evolve. That leads just to a rough idea of what you would expect the dark energy to be, which is roughly what we see, but you can't, by this kind of reasoning, known as anthropic reasoning, come to any precise predictions and in that way verify the speculation. What we really need to do is to extend our measurements at very large distances and find out whether the dark energy is really constant with time, a constant energy per volume, as we would expect according to anthropic ideas, or whether it is gradually decreasing, as we would expect if it's small because the universe is old. This is a major effort now, which is exercising the time and money of many astronomical groups. And by the way, and just in closing, I would say this is another area where science at the very large and very small come together. They're both very expensive. To go farther into the very small distance scale, we need larger accelerators. We just don't know any alternative. They're getting very expensive, very hard to sell to governments. Observations that will determine the evolution of the dark energy are expensive. They involve enormous ground-based and often space-based observatories whose cost is beginning to approach the cost of large accelerators. We hope that the interests of the public in this kind of science will be sufficiently aroused so that governments will feel impelled to continue to support this kind of fundamental research. And I hope that occasions like the Moscow Science Fair will add in their way to the support for science that we hope will continue in the years to come. Thank you very much. Spasiba. I'll be happy to take questions if that's technologically possible. Hello, are there questions?
Будут вопросы или?
We have questions for you.
Okay.
The first question is from Maxim Maltsev. Dear Professor, when do you think a unified model in physics will be created, which will combine gravity and the standard model into the unified theory? What problems are there at the moment?
Well, of course, I don't know. We've been hoping for that now, for a unified theory of everything. We've been hoping for decades, and progress has been very slow. In a sense, some of the difficulties that we saw earlier have been overcome. We used to say that the way that in the standard model, we have learned how to cancel the apparent infinities that we encounter in our calculation. A method known as renormalization, which cancels infinities with a redefinition of the constants of the theory, that wouldn't work for gravity. And that was a fundamental reason for doubting that quantum mechanics would even apply to gravity. We don't feel that way today. Gravitation has been brought into the same framework of quantum mechanics that we understand the other interactions of nature. But unfortunately, with that understanding, we also learned that we don't know the physics at the scales of distance, the very small scales where gravity becomes a strong force. There are speculations about that. I would say there are two leading speculations of theories that would combine gravity with what we already know in the standard model. One goes by the name of asymptotic safety, which preserves most of the structure of quantum field theory with one important modification. I don't want to take time to go into it. The other is a really new and exciting mathematical development known as string theory. Well, it's not so new now. It goes back to the 1980s, but it's extremely beautiful. It offers the promise of unifying everything. It makes gravity necessary. You could say that's the one successful prediction of string theory, is that it predicts the existence of gravity. But there has been essentially no progress in recent years in applying string theory to making predictions that we can then verify. I don't know the answer to your question. Democritus, as I said, speculated about atoms, and that was 2,200 years before we really became sure that matter consists of atoms, and we learned their size and mass and other properties. So perhaps we have 2,200 years to wait before we really understand physics at the deepest levels. I'm betting that's not true. What we desperately need is a shove, a push from new experimental data. But as I said, that's expensive, and we rely on government to supply the facilities that can provide that sort of impetus to science. I'm afraid that's not a very satisfactory answer, but this is not a very satisfactory situation.
We have a second question from Nikolai Yermilov. Dear Professor, what do you think about the future of M theory?
Well, M theory is, it's a name given by Edward Witten to a general approach out of which it was thought string theory would emerge. I haven't worked I mean, since that was introduced, I haven't worked on string theory. I did a little bit when string theory was first introduced and made no progress. I mean, clearly M theory has not led us to the final answer, but, you know, there's an old joke about someone who keeps playing poker, a card game, and with people who always take his money. And he's asked why he goes on playing with them when he always loses his money. And he says, I can't help it. It's the only game in town. Well, M theory in a way, or string theory, which is essentially the same as M theory, is in a sense the only game in town. It is the most attractive direction for speculation, and but it hasn't gone very far, and it's very disappointing. But you know, this has happened before, not just going back to Democritus, but going back to the 1950s. Yang and Mills developed a theory that they hoped would apply to the strong interactions, a theory patterned after electrodynamics, but more complicated. And for a while, it was thought the Yang-Mills theory was hopeless. It led to ridiculous predictions like new massless particles. It turned out that it's an essential part of what became our present standard model. It took, in that case, more than a decade for the Yang-Mills theory to be incorporated into a theory that could actually make useful statements that could be compared with observation. String theory now has gone more than one decade without that kind of achievement, but perhaps we shouldn't be impatient, just as I think the physicists who were impatient with Yang-Mills theory were probably mistaken. Well, in fact, we know we're mistaken.
And we have another one question. Dear Professor Stivен Uайнберg, what is the connection between macrocosm and the origin of life? Thank you. Sincerely yours, Valentina Ivanovna. And thank you for your books.
Well, you're welcome. Thank you for mentioning my books. The origin of life is something that I have no useful ideas about. The big question, I suppose a big scientific question is assuming a planet where conditions are favorable, and we know there are billions of them even in our own galaxy, not to mention all the other galaxies. What is the probability of life arising? I haven't got any idea. I think there is, perhaps though, in your question, there's a deeper question. Does that involve new physics? I don't mean new physics just in the sense of new physical ideas, new ways of doing calculations. Does it involve something new in the laws of physics themselves? And there I have to make a guess. Obviously, I don't know because I don't know how life arose. But I would guess very strongly that the answer is no, that there is nothing about life that is built into the laws of physics, except, of course, that the laws of physics are such that they lead to nuclei and atoms and chemicals and all the other things which in the end are necessary for life. But if we knew the laws of physics at the deepest level, we wouldn't find anything in them referring to life specifically. And I don't have any proof of that, but that's been the whole history of science. The whole history of science has been toward a more and more impersonal view of nature, a view in which not only human beings, but life itself does not play a central role, except for those of us who happen to be alive. The greatest step in that direction, of course, was taken by Charles Darwin, who showed how out of millennia, hundreds of centuries of millions of years of breeding and eating, inheritable variations that occur through chance could nevertheless lead toward development of species that are better and better adapted to their environment and ultimately lead to us. Without any plan, without anything in the laws of nature that called for human beings to be necessary. After Darwin, science progressed further and we learned the chemical and physical basis for the heredity that stood at the basis of Darwin's ideas. We now know how that works, how genes work. As we go deeper and deeper into our understanding of life, we see less and less a sign of any plan built into the universe at a deep level. We see more and more the workings of impersonal laws of physics and historical accident. But as to the origin of life, well, I wish I knew.
Thank you so much. And I think we don't have any more questions from the live audience. But we have one video question. Just a second, please.
Well, I wish I was there with you in Moscow. I had a very nice visit to Moscow many years ago. And I appreciate you giving me this opportunity.
Мне были незабываемые впечатления. И, конечно, спасибо вообще за то, что пригласили меня выступить. Спасибо за внимание.
Здравствуйте, меня зовут Олеся Ловицкая, я ученица 9 класса, и у меня такой вопрос. Что предсказывает наука? Если две черные дыры сольются в одну, как изменится их масса, энергия и гравитация?
What happens at the merger of two black holes? That is the question.
I'm sorry, I thought we were done.
What happens? Я вообще полагал, что мы закончили, или мы не закончили.
I'm sorry, it's now past the hour, and I have to leave, so I will say goodbye.
Мне нужно уже прощаться. Прошу прощения. До свидания.